We've introduced the idea of differential equations before, but I wanted to be a little bit more formal in this video in terms of the notation that we tend to use and the method in which we go about solving these. A differential equation, or you'll sometimes see this abbreviated and just called diff-EQ, remember, is an equation that involves a derivative somewhere in it. Sometimes, like what we've done before, the derivative is isolated and we have dy dx equals secant squared plus 2x plus 5, and we want to just figure out what function has that as a derivative. Or we could have dy dx is not isolated, y squared times dy dx equals x. And what we've done in the past with those is we've gone ahead and isolated dy dx and then done our antiderivatives. And that's still a way that works relatively frequently, and we tend to use a lot. But it's not the only way of approaching it. One way to approach it is to think of this in terms of solving equations like you're used to from algebra, where we want y's on one side, x's on the other. In other words, we want to just separate our variables. So in the case of our first example here, to get the y's on one side, x's on the others, remember dy and dx are differentials that I can multiply. And we always want to move things by multiplying or dividing. We don't want to add or subtract on these. Always multiply or divide. So I could multiply each side by dx, and I would have dy equal to quantity of secant squared plus 2x plus 5 times dx. Now in front of the dy, there really is a 1. And some people like to write that in there, but it's not required. But now I want to undo the derivative part. And we've learned with the fundamental theorem of calculus, specifically FTC part 1, that the inverse of derivatives is integrals. So to undo the derivative, I'm going to take the integral of each side. Now, this is a little bit different in the integrals we did last unit in that, if you notice, I don't know the bounds for this because all I have is a derivative. I don't have any initial condition that I was given. And when we have no bounds, this is called an indefinite integral. And we approach it in the same way. So for example, the integral of 1 dy is saying, I want to know what's the antiderivative of 1 with respect to y. In other words, y is my variable. Well, that would be y. But now technically there is a plus c. Remember, the only time we can ignore plus c on antiderivatives is when we're doing definite integrals. And these are indefinite because we don't know the bounds. Now my equal sign, antiderivative of secant squared with respect to x is tangent. Antiderivative of 2x would be x squared. Antiderivative of 5 would be 5x. And then because it's an indefinite integral, plus c. Now technically I do need to isolate the y, but if I subtract a constant from each side, I will get y by itself here, but I'm still going to have some constant because these are not the same c's. They're different constants. So typically, we only worry about putting the plus c with the side with the x's. And here, if you remember, is what we call the general solution. If I wanted to know what c is, I would have to be given a point, and then I could find the particular solution. But now this method works. This method here, using an indefinite integral, if we already have dy dx by itself, it doesn't tend to really come up very often. However, where we have dy dx not isolated, this is where using separation of variables, where we get y's on one side, x's on the other, tends to come up. So to get y by itself and x by itself, I would need to multiply by dx. So I'll have y squared dy equals x dx. Integrals are the inverse of derivatives. Well, the antiderivative of y squared with respect to y would be 1/3 y cubed. I'm going to worry about just putting the plus c on the right-hand side with the x. I'm not going to worry about putting it with the y's. Antiderivative of x with respect to x is 1/2 x squared. And then my plus c. Multiplying by 3, y cubed equals 3/2 x squared. C times 3 is still a constant, so it's just plus a constant. And then taking the cube root, y would be the cube root of 3/2 x squared plus some constant. And there is our general solution. Now, if I wanted to actually know what c is, I would have to be given some initial value that my function has to go through, and that's what's called an initial value problem. So it just gives us our particular solution that allows us to find what c is. So here, if I'm dealing with the differential equation dy dx equals e to the x minus 6x squared, and just for practice sake, I'm going to do this by separating the y's and x's. So multiplying each side by dx would give me 1 dy times the quantity, or equals the quantity of e to the x minus 6x squared times dx. Derivatives are and integrals are inverses of each other, so I'm going to take the indefinite integral of each side. Antiderivative of 1 with respect to y is y. I'm just going to worry about putting the plus c on the right-hand side. Antiderivative of e to the x is e to the x. Antiderivative of 6x squared would be 2x cubed. And then plus c. And then I can use this information that our function must go through 1, 0, and plug this in to find out what c is. So I would have 0 equals e minus 2 plus c. So c was equal to 2 minus e. And so our function is going to be y equals e to the x minus 2x cubed plus 2 minus e. There is our particular solution.